In the last video, we looked at what happens when limits go to infinity or when the x is going to infinity in a limit. We saw that the function goes to infinity when there's a 0 in the denominator, but there's a set number in the numerator. We also saw one example where we had a whole, and in that case we saw there's a 0 both in the numerator and denominator at the start. We could simplify the fraction. So I want to dive more into that idea. Just because we see a 0 in the denominator does not mean that the function is going to infinity or negative infinity. It could be that the function is what we call an indeterminate form, and that means we need to do something else to determine what's going on. If there's a 0 in both the numerator and denominator, that is not saying that the function is going to infinity. So let's take an example. Let's say that we have the function x squared minus 7x plus 10, and it's over x minus 2. I want to find the limit of this thing as x goes to 2. So of course we'd have the limit as x goes to 2 of the x squared minus 7x plus 10 over x minus 2. And right away we see that if we plug this 2 in, we get 0 in the denominator. And so for half a second we might think, oh, it might be a vertical asymptote. It's going to have positive or negative infinity. That might be true, but we also need to check that numerator. So if we take the 2 and plug it into the numerator, we get 4 minus 14, negative 10 plus 10. Well, we get 0 over 0. And that's not saying it's going to infinity. Just because there's a 0 in the denominator doesn't mean it's going to infinity. This is what we say of indeterminate form, means we can't determine what it's doing right now. Now, the book doesn't actually define indeterminate form yet, so I'm kind of giving you a little bit of a sneak peek on what we'll see in the future. But if we see 0 over 0, we can go ahead and formally name it. It is of indeterminate form. So what this tells me to do is to look for something else I can do to this fraction. And we know that anytime we can simplify, we can factor things out, we potentially can simplify. So can we factor the numerator? Well, yeah, we can. X minus 2, x minus 5. And lucky enough for us, those x minus 2's are the same, so we can actually cancel them out, leaving us the limit as x goes to 2 of x minus 5. And now we see when we plug that 2 in, well, 2 minus 5 is just negative 3. And so we defined this in the last video as a whole, but we see that we can do that extra step. We can continue to do math on this thing, and we actually do end up with a limit value that's not just plus or minus infinity. So this is a very common trick. Anytime we see that 0 over 0, that indeterminate form, this is one of the tricks we're looking for. If we have a polynomial over a polynomial, we can always look for factors, and we can look for these things to cancel and to simplify. Now that is one trick of several that we're going to see. So let's go over some of the different tricks that we might have. Let's find another limit. Let's find the limit as x goes to 0 of 1 over x minus 1 plus 1 over x plus 1 over an x. So if I look right now, I see that plugging in 0 gives me 0 in the denominator. I might think for half a second it's going to be an asymptote. But if I look for a further second, I see I get 1 over negative 1, which is negative 1, plus 1 over 1, which is 1. Therefore, right now I'm getting a 0 over 0, meaning the fraction is in indeterminate form. I need to do something else to figure out what this limit actually is. So let's try and figure out something I can do. Well, I know I never like fractions and fractions. Let's clear those fractions. And so if I think about what it's going to take to clear those fractions, I need to multiply by the common denominator. You could also get a common denominator in the top and then multiply by the reciprocal. I can't multiply by the reciprocal right now because I don't have just one fraction over one fraction. But I think the faster thing to do is to multiply by the common denominator. When I say the common denominator, I'm looking in the numerator and the denominator, and I'm saying across both of those, in the numerator, what is in the denominator of the numerator? Well, an x minus 1 and an x plus 1, so I'm going to multiply by that. What's in the denominator's denominator, the bottom of the denominator, is just 1, so this should work. I'm going to multiply that on both top and bottom. And so when we do that, Still going to have our limit in front. Remember, we've got to make sure we're keeping track of that limit the whole way through. When we multiply the first fraction, the x minus 1s would cancel, leaving us an x plus 1. When we multiply the second fraction, the x plus 1s cancel, leaving us an x minus 1. And then in the denominator, nothing cancels, so we have now all three factors. So it's looking better. It's not a fraction and a fraction anymore. But I want to continue cleaning this thing up. Even if we're going to try and plug in, I haven't canceled anything yet, so I know it's still going to give me 0 over 0, but it'd just be a lot nicer to clean it up. So I notice there's some like terms across the top. So I have x plus x, which is 2x, and I have a 1 minus a 1, which is just 0. Now I'm not going to multiply out that denominator because I want to leave it as factors. Factors are the things that cancel. That's like the first example, we got everything into factored form so that we could cancel things out. I did simplify the top just because right now they're not factors, they're terms. And I wanted to simplify all the terms as much as possible so that I might be able to factor. And now I see that I do in fact have the x's factor, the factor of x is the same on top and bottom, so I can cross those out. I couldn't do that in the step above because I had the 1s there too. I couldn't cross out the x's. I had to wait till I had just the x term in the top. And so now I have the limit as x goes to 0 of 2 over x minus 1 times x plus 1. And that x in the denominator that is giving us a problem initially is gone. So now when we plug in, we should see that we end up with something that isn't just 0 over 0. And so in the top, clearly we have just the 2. In the bottom, we now have a negative 1 times a positive 1, which is negative 1. And once again, like with our first example, by doing a little work at the front, we've gotten to a point we could just plug in and we get a limit value of negative 2. So now kind of two tricks that we've gone over. If we have just polynomial over polynomial, our first example, we always want to try and factor. That's always a useful step. Factoring can always simplify things. If we have fractions and fractions, well, we've known since kindergarten that we don't like fractions and fractions, so we want to clear those out. We do that by multiplying by the common denominator. Let's look at yet another example. Let's take the limit as x goes to 4 of 4 minus x over, we'll have 5 minus the square root of x squared plus 9. So now we have a radical here. That's not catching my eye initially. My first instinct is just to plug in, right? That should always be our first instinct. So we plug into the top, we get 4 minus 4, which is 0. Well, 0 is perfectly fine in the numerator. 0 over anything other than 0 just means we have a limit of 0. That'd be really nice. We'd be done already. But let's see what happens in the denominator. Denominator, we have 5 minus, we'd have the square root of 4 squared is 16 plus 9 is 25. Well, the square root of 25 is 5, and so we have 5 minus 5. Well, now we have a problem. We have 0 over 0. We're back to the indeterminate form. 0 in the numerator alone is never a problem. It just gives us 0. 0 in the denominator alone gives us one of the infinities. 0 over 0 tells us we have more work to be done. And so on this one, the trick is going to be to rationalize. And we are pretty comfortable with rationalizing denominators. I will go and tell you sometimes that there will be a square root in the numerator and we'll get that 0 over 0. If there's a square root in the numerator, we can rationalize the numerator the same way we can the denominator. So anytime we see a square root, I don't rationalize right away. I make sure I get 0 over 0. But when I have a square root and I see I have 0 over 0 in determinate form, now I'm going to rationalize. I'm going to multiply by the conjugate. So the conjugate is whatever we had, just with the sign switched in between. So we're still going to use the 5 in the x squared plus 9 under the square root, but the symbol between them I'm placing is a 5 plus square root of x squared plus 9, where the plus 9 should still be under the square root. So now let's see what we get when we simplify. Well, like what we saw in the last example, I'm not going to actually distribute the 4 and the minus x right away. I'm going to leave it for just a second because I like factors until I've convinced myself that things aren't going to factor cancel like I would want. I'm not going to bother multiplying that or foiling that together. However, in the denominator, because this was the thing I was rationalizing, this is the square root I want to move, this one I am going to multiply out because by choosing the conjugate, it should work out to be really, really clean. So we have 5 times 5, which is 25. Then we know that center terms are going to cancel because they're a conjugate, so we have 5 times the radical, and then we have the negative radical times 5. Those center terms will cancel, and then we have the square root times the square root, which cancels the square root and just leaves us what's on the inside of the square root. So we'll have the x squared plus 9, but there is a negative still in front. In that denominator, I don't have very nice factors yet, so I'm going to continue to simplify. The numerator, I'm still hoping that one of these factors will cancel, namely the 4 minus x, because that was the thing giving me 0 before. So let me clean up that denominator. Well, 25 minus x squared minus the 9, well, 25 minus 9 would give me 16 minus x squared. Well, nice, it's simplified, but it's still not canceling, but 16 minus x squared should be jumping out at me. That is the difference of squares. That can be factored. We always want to be on the lookout for things to factor. So we have our limit as x goes to 4. And we still have the 4 minus x in the numerator. We have 5 plus square root of x squared plus 9 in the numerator. And then when we factor the difference of squares, we're going to have the square root of 16, which is 4 minus x. And we have the square root of 16, or 4, plus the x. And now we see that those factors do in fact match, so they will cancel. That should cancel off that problem of 0 over 0. Those were our zeros. So the limit as x goes to 4 of 5 plus the square root of x squared plus 9 over 4 plus x. And so let's see what happens now when we plug in. So we'll have 5 plus square root of 16 plus 9 over 4 plus 4. 16 plus 9, 25, and square root of 25 is still 5, as we saw before. So we have 5 plus 5 over 4 plus 4. 5 plus 5 is 10, 4 plus 4 is 8, and we can simplify that to 5/4. And so once again, we started with something where we had 0 over 0 in determinate form. We've been able to work it to a point that we actually do end up at a set value. We get 5/4. We found its limit. So 3 tricks we've seen so far. We want to always look for factorization. Actually, we use that again in this problem. We actually use 2 tricks kind of in one. But we want to look for factorization. We also want to look for fractions and fractions to simplify, and we can do that by multiplying by that common denominator. And then anytime we have radicals, we always want to simplify those radicals using the conjugate, and then we can clean it up from there. Now there's going to be one last trick that we're going to see. This trick relies on a theorem. And the theorem says the limit as x goes to 0 of sine x over x, this is equal to 1. And there's a formal proof, but I'm just going to kind of give you the idea behind it. If we think about the sine function, we know what the sine wave looks like. Looks approximately like this. Well, sine's kind of an interesting function that if we get really, really close to 0, we're to look at this section right here and kind of blow that up, and we're to keep zooming in and in and in, it actually looks pretty straight, right? If I look at that region right there and I continue to zoom in more and more and more, it looks like a straight line, and that line would have just a function of x. And so sine x immediately around 0 could be modeled just by x, and so we have x over x, which is, of course, just equal to 1. So again, not going to do the formal proof, but let's just take some examples of this and let's find some limits. So let's say we have the limit as x goes to 0. And notice that is key. The x has to go to 0. If it's anything else, well, 1, the denominator wouldn't be zeroing out, but 2, it does need to be going to 0. So if you end up with something like 2 minus x where it's going to 2, well, we can't just say, hey, sine of x over x is equal to 1. It has to be going to 0. So limit as x goes to 0 of sine 3x over x. Well, this doesn't go to 1 because this theorem here is saying that the angle has to match exactly by what it's being divided by. So remember, inside the sine is the angle. This angle is always in radians, but the 3x has to match exactly with what's down here, and that's not true. So we need to get it to match, because right now if I were to plug in that 0, I should always do that first to show that it is in determinate form. Sine of 3 times 0 is sine of 0, which is 0, and 0 on the denominator is just 0. So we see that we have an indeterminate form. We have to do something with it. But if we want to use this theorem, we need these two things to match. So let me just add a 3 here, or really multiply a 3 here. I can't just go multiplying on the bottom without doing it on the top, so I can also multiply a 3 here. Well, that's looking better because now they do in fact match. And this 3 here, I know using my limit laws, I can just pull it to the front. So I'd have 3 times the limit as x goes to 0, sine 3x over 3x. And that limit I know is just equal to 1. And so we're left with 3. That is relatively simple. Let's take another example. Let's look at the limit as, I'll switch up variables, I'll call it h, as h goes to 0, of h over sine 3h. Well, kind of the same as before, where we have that 3 there. So we would think, hey, we need a 3 on the other side too. But the bigger problem is that sine is not where it's supposed to be. This is completely upside down from where it's supposed to be. But I'm going to do kind of the same trick. First thing I recognize is this is equal to 0 over 0. I know that if I had the limit of sine 3h over 3h, that would be equal to 1. And that would take care of this problem of 0 in the denominator. So I'm going to just divide this by 3h. Well, I can't do something to the bottom and not do it to the top, so I can divide this numerator by 3h as well. Remember, with limits, we're able to compute these fractions separately. So I'm going to write this out as the limit of the numerator, the h over 3h, divided by the limit of the denominator. Well, the numerator, I'm still getting 0 over 0, except I realize that I can cancel out those h's. And so we'll be left there with just the limit as h goes to 0 of 1 over 3. The denominator, however, we have exactly that property that we set up at the beginning, so that's just equal to 1. And so we're left with a limit of 1/3. Again, pretty easy. We just have to figure out how to get that exact format that we want. So it has to be sine of the angle over itself. It has to be that identically every single time. Now, what we saw here is it actually doesn't matter whether the sine is on the top or the bottom. We would have ended up the same way if we had just put a 3 with the h here and a 3 here. We would have ended up with that 1/3. We can very formally show it by getting that sine of the angle over itself every single time. Let's do one last example. Let's take the limit as x goes to 0 of cosine squared x minus cosine x over x squared. So first step would be to plug in the 0. Cosine of 0 is 1, cosine of 0 is 1, 1 minus 1 is 0, and then through in the denominator we get 0 over 0. Indeterminate form tells me I need to do something else. Now this one looks nothing like what we've had before. We're supposed to have sines, not cosines, and we can't just say if sine x over x is equal to 1 that cosine x over x is equal to 1. That'd be completely false. If we think about what cosine looks like that. That doesn't look like 1 to me. That doesn't look like a slope of 1. It doesn't look like it's close to x. So we're going to need to figure out something else to do. If I have cosines, I need sines. So we're going to have to figure out how to get there. Now the first thing I realize though is that I can factor out a cosine from the numerator. It always helps to factor. We saw that in the very first example. So I can factor out the cosine x. I'd have cosine x minus 1 over x squared. Now, it doesn't really cure my 0 over 0 problem, but it's just helping me see what it looks like a little bit better. I know I need some sines. If I'm going to have this x here kind of cancel out, or if I'm going to be able to pull it out with something so it goes to 1, it's going to have a sign in the numerator. I can't just go sticking a sign in the numerator. It's not going to be as easy as the last case where we just multiplied top and bottom by 3. Problem is if I multiplied a sine x on top, I have to do it in bottom. So sure, I fixed the sine x over x, one of them becomes just a 1, but I've added yet another 0 in the denominator. So what I'd really like to do is, because this cosine x minus 1 is giving me a 0, I'd like that to go away as well. So I need to change this to a sine. A few different ways we can do it. We could use a half angle formula or a double angle formula. I a lot of times prefer to use my Pythagorean identities. If I could somehow get this to become a cosine squared, well then cosine squared can somehow become a sine squared. So I'm going to multiply, and notice we had a cosine squared at the beginning, but we also had that cosine, which doesn't fix my problem. Cosine of 0 here is not a problem, that's just 1. This is my problem, and I need to turn this somehow into a sine squared. So what I'm going to do is I'm going to multiply by the conjugate. I'm going to multiply by the cosine of x plus 1. That's going to give me a cosine squared term there without adding in another cosine term. I'm going to do that on top and bottom. So let's see what happens. I still have my cosine x in front. That's not causing me any problem. But now when I multiply these two binomials together, I get a cosine squared, which was my goal. I also don't create new cosines because I have a plus cosine minus cosine cancels. I have a minus 1. On the bottom, I have an x squared times a cosine x plus 1, and that's also not causing me any problems because this is just 2. This cosine squared minus 1 is still causing me problems. That's still a 0 over a 0. So let's think about what we can do with that. Well, I know that cosine squared can be written as a sine squared. Now this is going to be, cosine squared minus 1 is going to be a negative sign, but that still is helping me. It's getting me in the right direction. And that's using our Pythagorean identity. And so now we're at this point, and we're very nearly done at this point, even though it doesn't look like it. Let me fix this. X was supposed to be going to 0. So sine x over x is equal to 1. Well, conveniently enough, we have a sine squared here and we have an x squared here. So there, we can break this up into that pairing. I'm going to kind of rearrange this a little bit. The negative can come to the front. So this negative here I'm dragging to the front. The cosine x over the cosine x plus 1, none of that was causing me any problems. I'm going to break off into its own the sine x over x and another limit of sine x over x. This front limit, no reason I can't just go ahead and plug in, so we'll have a negative cosine of 0 over cosine 0 plus 1. That should be a times, not a plus. Then we have a times 1 for this limit. Then we have another times 1 for the second sine x over x. Cosine of 0 is just 1. So we have 2 in the bottom times 1 times 1. So that's just going to give me a negative 1/2. And so there is our limit. That one, I think, definitely the most complex example we've done in this video. But those show you the tricks. Going back to the very first example all the way up here, we always want to look for factors. And if we can factor out those factors, we want to do so. Go up a little bit further. Factoring out factors helps. We cancel out those factors, and then we can hopefully plug in and simplify. We have fractions and fractions. We want to multiply by the common denominator, get rid of those fractions and fractions, simplify, and we can get to our limit. If we have square roots and we're getting that indeterminate form 0 over 0, multiply by the conjugate. Doesn't matter if it's top or bottom. Simplify, we might have to do some factoring. Simplify, and we get to our limit. If we see that we have trig functions and we have that indeterminate form, and again, all of these pertain to indeterminate forms. If we see trig functions and we just get 5 over 3, great, our answer is 5 over 3, we don't need to do any of this extra work. Or if we see a square root, we plug in and we get 2/3, great, we have 2/3, we don't need to do any work. But if we see trig functions, we should be on the lookout for this sine x over x. Might be we have to do a little manipulation. Might be that we have to completely change trig functions entirely. But anytime we see that we have those trig functions and we're getting 0 over 0, we should be on the lookout to try and get to a sine x over x.